This video is going to review the different types of intermolecular forces that exist between particles. These are the forces that hold particles together either in the liquid state or in the solid state. We just got done doing gases and learned that in ideal situations, gas molecules don't interact with each other. Well, in liquid and solids, we have a lot of interactions. So these interactions are referred to as IMFAs, intermolecular forces of attraction. And so you can imagine that the individual molecules or atoms or ions, whatever it is we're looking at, it depends on the type of material, can represent individual bricks in a wall. And the IMFAs are really the mortar that helps keep the bricks together. So we have these individual bricks. They could, again, be atoms, they could be ions, they could be molecules. In this case, let's use a very familiar molecule, water. And so the covalent bonds that hold an individual water molecule together are called intramolecular attractions within a molecule. The intermolecular attractions are the ones between one molecule and another, or one atom and another, so between the bricks. So these attractions are what holds hydrogen and oxygen together between water molecules in an ice cube, let's say. So different types of IMFAs. If you remember, there were 6 of them that we learned first year. We're going to look at those same 6 again this year. From weakest to strongest, London forces, or sometimes called London dispersion forces. Dipole-dipole attractions, hydrogen bonding, metallic bonding, ionic bonding, and finally the strongest, covalent network. So hopefully these ring a little familiar to you. Another term that you're going to see as well is the idea of van der Waals attractions. Yep, same guy from the gas unit. So the idea that in a liquid or a solid, you have attractions between molecules, and that's what holds the substances together more tightly and prevents them from being influenced so easily like a gas can be from pressure or temperature or something like that. So let's take a look at, or refresh your memory at least, at what kinds of substances have these different interactions. So starting with London forces, those are the weakest, and those bonds, those kinds of intermolecular forces occur between nonpolar molecules and between noble gases. So we're going to get into details of all of these eventually, but we just want to kind of do a summary here. Dipole-dipole attractions are between polars. So here you have molecular substances, nonpolar ones versus polar ones. You also have another little subset for London forces, noble gases. And then finally, hydrogen bonding is really a super strong polar molecule. And if you remember, the way to get a hydrogen bond is you have to have hydrogen directly bonded to H, O, or N. It can't be hydrogen to carbon and then carbon to oxygen. It doesn't work that way. Hydrogen has to be directly bonded to either fluorine, oxygen, or nitrogen. So all 3 of these are what happens when you have molecular substances, things that are covalently bonded. Then we've got metallic bonding is what holds metal atoms together. Ionic bonding is what holds cations and anions together in your crystal lattice. And then finally, covalent network. This is a really different kind of IMFA. I hesitate to even use that because really a covalent network bond is a true covalent bond. What you're going to see, it occurs in only certain types of atoms, and what you wind up with is a very big network of atoms bonded to each other. So again, we'll get into a little bit more detail as we move on. All right, so let's take a look at some of the ones that are already familiar to you. So I'm not going to do these examples in order of weakest to strongest. We're going to do them in terms of what we're most familiar with. So the ionic bonding stuff is one that we're very familiar with. So if you remember, the structure of an ionic bond, or the structure of an ionic compound, is really a three-dimensional lattice of cations and anions. So you have alternating charges. So here you can see the big ones are chlorine, the smaller ones are sodium, and they are kind of packed in a crystal nice and tightly, where you have the pluses surrounding the negatives, and then you have the negatives surrounding the pluses. Like I said, it's a crystal lattice of alternating cations and anions, something from the left of the periodic table with something from the right of the periodic table, metal and a nonmetal. So if you look at a substance and there is not the cations there, or there's not a metal and a nonmetal, there's no way it's going to be ionic bonding. And so let's review the idea of lattice energy. We've talked about it before, but let's just do it again. Lattice energy is the energy released as ions form the crystal. So we're putting all of these crystals together, or all of these ions together. Bonds are forming, attractions are forming, and as those attractions form, they make the substance more stable, and so then that energy gets released, which is what we call lattice energy. So properties of ionic compounds, if you think about what you've learned, they're hard, but they're brittle. So why is that? Next slide is going to show you. They are non-conductive when they're a solid because the ions are stuck in place as a solid, but they are conductive if you melt them or dissolve them, because then the ions are free to move. Remember that a conductor is something that allows the flow of charged particles. And so if we melt an ionic crystal, the ions are free to move. If we dissolve an ionic crystal in water, the ions again are free to move. So those are probably the big ideas in terms of ionic compounds. All right, so let's talk about this why hard but brittle. So remember that the crystal is alternating cations and anions. So you've got the negative, in this case chlorine, surrounded by, on all sides, by the positive sodiums. Alternating. Okay, but what happens if I apply a force to the crystal? It's going to cause part of the crystal to shift. So now look what we have here. We have a layer where the negative and the negative are adjacent to each other. The positive and the positive are adjacent to each other instead of the opposite. And what's going to happen? You're going to have repulsion. So the second you shift that crystal structure, you have the shattering of one part from the other because of that repulsion. So that's why they're hard. But if you apply a force just right and get that crystal to shift, you can get it to shatter. And remember, once again, Coulomb's law coming up again. Lattice energy can be controlled by Coulomb's law. Remember the two big ideas. Charges and sizes of ions are what really matter in terms of keeping them together. You want a short distance in order to have a big force, and you want a big charge in order to have a strong force. At this point, I'm guessing we don't have to go over this too much, so I'm going to move ahead. Another thing we've seen already is the idea of the Born-Haber cycle, but it comes back in to taking a look at things. Remember that the Born-Haber cycle is the way that we show how lattice energy can be calculated in terms of what has to happen to the atoms and so forth. All right, so then that takes care of the ionic stuff that we want to talk about. We'll get into metallic bonding next. If you remember, in a metallic structure or in a metallic substance, you have a lot of nuclei arranged in a regular grid or a regular matrix. But then you have a sea of delocalized electrons. The valence electrons are free to move throughout that grid. And so these guys are going to flow all around. I thought this was a video, but maybe not. These guys are going to flow all around. No electron stays with any one particular atom. They just move constantly. So a metallic bond is stronger than all the van der Waals, but generally it's weaker than the covalent bonds and the ionic bonds that we've seen, because there's not a specific pairing of electrons like you saw in a covalent bond, or like you saw in ionic bonds, where you have all those pluses and minuses with the strong charge attraction. So the result of this sea of electrons results in properties that you are very familiar with. The surface is very shiny. You have the electrons constantly moving, so you have light interaction going on. It's conductive, both thermally and electrically. It's strong, it's malleable, means we can pound it into flat sheets. It's ductile, means we can stretch it into long wires. That's because it doesn't matter if these, so unlike the ionic crystal, if we apply a force, the only thing that's going to happen is it's going to shift some of the rows of nuclei, essentially. And the fact that all the electrons are just kind of free-flowing, it doesn't matter where the nuclei are. So nuclei are, that sounds like an odd phrase. So you can actually stretch this out and take this from being 4 by 4 to being 2 by 8 or 1 by 16, doesn't matter. So that's why we can do all sorts of manipulation with the thing. All right, and then finally the last idea, the idea of an alloy. Alloys, if we were limited to just the elements on the periodic table that are metals, there's not a whole lot of properties there. So what we do is we mix elements in order to create alloys with new properties. Now, the one important thing is they still have metallic properties. You may not have all atoms being metals. For example, carbide steel has carbon mixed in with the iron, but you have metal properties even if there are nonmetals there. Two kinds of alloys: substitutional alloys, where you have similar size atoms simply replacing each other in the grid, or you have an interstitial alloy where you have little atoms kind of pushing themselves inside or in between the bigger atoms, so you have a much tighter fit. Brass, if you remember when we did the pennies first year, brass is an example of a substitutional alloy. Steel is really the only type of interstitial alloy that I can think of. So again, if you think of carbide steel, the carbon atoms are going to fit in between the little iron. The little carbon atoms are going to fit in between the iron. All right, so I think we're going to quit here because we're running out of time and we got to go on and do a couple of others, and I don't know if I'm going to have enough tape to do that. So we'll stop here and pick up covalent bonds in part 2.